Somewhere out there, a black hole, the mass of a mountain but smaller than a grain of sand, could be silently passing through our solar system right now. It was created before any star, before any galaxy, before any atom as we know it. These are not the black holes astronomers usually study. Those form from the collapse of massive stars, colossal and predictable. This is something else entirely, a primordial black hole, a hypothetical object born in the chaos of the Big Bang itself. If they are real, they could solve one of the biggest unsolved problems in physics: the nature of dark matter. Ordinary matter, the stuff of planets, stars, and us, makes up only about 15% of all the matter in the universe. The rest, roughly 85%, is dark matter. We cannot see it, but we feel its gravity pulling on galaxies, bending light, shaping the cosmos on the largest scales. For decades, the leading explanation has been a new kind of particle, something like a WIMP, weakly interacting and massive. But after years of building ever more sensitive detectors deep underground, we have found absolutely nothing. No convincing signal, no candidate particle, no confirmation. That failure has forced scientists to reconsider ideas once thought fringe. One of the most radical yet stubbornly plausible is that dark matter is not made of particles at all. It is made of black holes. Not the kind we know, but ancient tiny black holes that formed in the first fraction of a second after the Big Bang, when the universe was a soup of energy dense enough to collapse directly into black holes without needing a star. These objects would be older than any star or galaxy, true cosmic fossils from the universe's infancy. They would be completely dark, betraying their presence only through gravity, which makes them perfect dark matter candidates. But that same invisibility also makes them incredibly hard to find. And here's the thing. We already have ways to look for them, and the search has begun. Astronomers have used telescopes to scan for their subtle gravitational effects, watching for tiny changes in starlight or the motion of distant objects. Yet so far, the results have been puzzling. They raise a deeper question. If these ancient fossils are all around us, why can't we see them? To understand that, we first need to go back to the beginning, to what we know about the missing mass of the universe. The evidence for invisible mass didn't appear all at once. It came piece by piece, each clue harder to explain away than the last. In the 1970s, astronomer Vera Rubin was mapping how fast stars orbit in spiral galaxies. According to Newtonian physics, the further a star is from the bright center, the slower it should be moving, just like outer planets in our solar system move slower than inner ones. Instead, Rubin found something baffling. The rotation curves were flat. Stars in the outer edges of galaxies were moving just as fast as those near the center. Something was holding them in place, something massive and invisible that extended far beyond the visible disk. The numbers were staggering. Whatever this extra mass was, it outweighed all the stars and gas by a factor of 5 to 1. Then came gravitational lensing. Massive objects warp the fabric of space-time, bending light that passes nearby. When astronomers looked at distant galaxies, they saw images being distorted by invisible mass along the line of sight. The distortions could only be explained if enormous amounts of dark matter were present in galaxy clusters, far more than the visible galaxies accounted for. And the final nail came from the cosmic microwave background. The faint radiation left over from the Big Bang shows tiny temperature variations that act as a fingerprint of the universe's composition. By precisely measuring those patterns, cosmologists calculated that ordinary matter, the stuff of stars, planets, and us, makes up only about 5% of everything. Dark matter accounts for roughly 27%. The rest is dark energy. So the problem is real. It's not a measurement error. Something is out there, pulling on the universe gravitationally, but it does not emit, absorb, or reflect light. it is, for all practical purposes, invisible. For decades, the most natural explanation was a new particle. Physicists had a perfect candidate: the weakly interacting massive particle, or WIMP. These hypothetical particles would interact only through gravity and the weak nuclear force, making them nearly impossible to detect directly. But they would be produced in the early universe in just the right abundance to explain dark matter. The theory was elegant, and experiments were built to catch them. Deep underground, tanks of liquid xenon and germanium waited for a telltale flash, a tiny recoil from a WIMP passing through. For 30 years, nothing. No convincing signal. The most sensitive detectors have now ruled out large regions of the parameter space where WIMPs were expected to hide. That deafening silence has forced the community to look elsewhere. And in 2015, something else happened. The Laser Interferometer Gravitational Wave Observatory, LIGO, detected the merging of two black holes. It was a historic event, the first direct detection of gravitational waves. But the masses of those black holes were surprising. Each was around 30 times the mass of our Sun. That might sound ordinary, but it's not. When a massive star collapses, it typically leaves behind a black hole up to about 20 solar masses. Stars between about 60 and 130 solar masses undergo a process called pair instability, which completely blows them apart, leaving nothing. So the mass range between roughly 20 and 150 solar masses should be nearly empty of stellar-born black holes. Yet LIGO found black holes right in that mass gap. They were too heavy to come from ordinary stars. One explanation is that these black holes were not born from stars at all. They are primordial, formed in the dense, chaotic first second after the Big Bang, when the entire universe was a pressure cooker of energy dense enough to collapse directly into black holes of almost any mass. If that's true, then LIGO didn't just detect gravitational waves. It may have already detected the ancient cosmic fossils we've been searching for. And that raises an obvious question. How exactly would these primordial black holes have formed in the first place? In the first second after the Big Bang, the universe was a seething, chaotic sea of energy, far too dense and hot for ordinary matter to exist. On tiny scales, it was not uniform. Inflation, the brief exponential expansion that preceded this moment, had stretched quantum fluctuations into patches of slightly different densities. These fluctuations acted like seeds. In some regions, the density was just a little higher than average. Think of the early cosmos like a bowl of batter being vigorously mixed. Dense lumps formed in the chaos, and if a lump was compact enough that its own gravity could overwhelm the fierce outward pressure of radiation, it collapsed directly into a black hole. No star, no fusion, no millions of years of evolution, just a catastrophic implosion. The mass of the resulting black hole was determined by the size of the collapsing patch at the moment it fell inside its event horizon. That size was set by the Hubble horizon at that time, which grew rapidly as the universe expanded. A region spanning a nanometer could produce a black hole with the mass of a mountain. A region the size of a star could produce one with the mass of 1,000 suns. This is why primordial black holes could span such an astonishing range. From less than 100 millionth of a gram, so tiny they would have evaporated almost instantly via Hawking radiation, all the way up to hundreds of thousands of solar masses. The smallest ones, with masses below about 100 million tons, are predicted to have completely vanished in a flash of high-energy gamma rays long before the first stars ignited. But for masses larger than that threshold, roughly the mass of a small asteroid, they would still be out there today, cold, dark, and invisible. The exact masses that formed depend on the details of inflation. Details we still don't fully understand. Different models predict different populations. Some produce mostly asteroid mass black holes. Others push into the stellar or supermassive range. That uncertainty is both a challenge and an opportunity. It means the search is not just about finding one black hole. It is about mapping the early universe's fingerprint by measuring the masses and abundances of these ancient relics. But if such black holes could form across such a vast range of masses, why have our telescopes found no smoking gun? The answer may lie in a strange prediction made by Stephen Hawking, a prediction that, if correct, turns the tiniest black holes into ticking time bombs. That strange prediction is Stephen Hawking's most radical legacy. In 1974, he showed that black holes are not truly black. Thanks to quantum mechanics, pairs of particles and antiparticles constantly pop into existence near the event horizon. Normally, they annihilate almost instantly. But if one member of the pair falls into the black hole while the other escapes, that escaping particle carries away a tiny amount of the black hole's energy. Over time, this leakage causes the black hole to lose mass, shrink, and eventually vanish in a flash. The effect is negligible for the stellar mass black holes astronomers usually study. A black hole with the mass of the Sun would take an unimaginably long time, far longer than the current age of the universe, to evaporate. But for primordial black holes with masses far smaller, Hawking radiation becomes the dominant clock. The smaller the black hole, the hotter it gets, and the faster it radiates. A black hole with the mass of a large asteroid, say 100 billion tons, would shine with a temperature of over 1,000 degrees and evaporate in less than 1 billion years. But for a primordial black hole with a mass around 1 billion tons, about 10 to the 12th kilograms, the story becomes truly dramatic. That mass is the sweet spot where the evaporation lifetime matches the age of the cosmos. If such an object formed in the first second after the Big Bang, it would be reaching the end of its life right now. And the end is spectacular. As the black hole shrinks, its temperature skyrockets. In its final moments, it doesn't just fade away. It releases a burst of high-energy gamma rays, a brief but intense fireball packing the energy of 1 million hydrogen bombs. The burst would be so bright that, if it happened within our solar system, our gamma-ray telescopes would detect it without any doubt. Even if the explosion occurred thousands of light years away, it would still stand out against the cosmic background. This gives us something priceless, a clear, testable prediction. If asteroid-mass primordial black holes are common enough to make up all of dark matter, then the sky should be littered with these final flashes. Gamma-ray observatories should be seeing them at a steady rate. But if the telescopes see nothing, that silence tells us something equally profound. It either means such black holes are extremely rare, or the primordial black hole population simply does not contain masses small enough to have evaporated by now. So, have we seen any of these ticking time bombs go off? That question leads directly to one of the most powerful instruments ever aimed at the gamma-ray sky. The Fermi Gamma-Ray Space Telescope carries the Gamma-Ray Burst Monitor, an instrument built to detect gamma-ray bursts, solar flares, and magnetar eruptions. But it can also look for something far fainter, the final flash of an evaporating primordial black hole. A black hole around 10 to the 12th kilograms would be finishing its evaporation right now, releasing a burst of gamma rays unmistakable from across the galaxy. If such objects make up a substantial fraction of dark matter, Fermi should see them popping off all over the sky. The Fermi team has searched. They have combed through over a decade of data, developing sophisticated algorithms to identify real evaporation events. These algorithms must filter out background noise, cosmic rays, and ordinary gamma-ray bursts. The result? Silence. Not a single confirmed primordial black hole evaporation. This no result is a powerful constraint. It tells us that any population of black holes below about 10 to the 15th grams, roughly the mass of a large mountain, cannot account for more than a tiny fraction of dark matter. If they were common, we would have seen at least a few flashes by now. The fact that we have not genuinely narrows the possibilities for the lightest end of the primordial black hole spectrum. But the null result only applies to those low-mass objects that would have had time to evaporate. Larger primordial black holes, above 10 to the 15th grams, would survive for billions of years longer. They are not exploding today. So Fermi's silence does not rule out black holes that are asteroid mass or planet mass. Those could still be out there in vast numbers, forming the dark matter we know exists. The gamma-ray search has eliminated the lightest branch of the primordial black hole mass tree, but the trunk and larger branches remain very much alive. That means we need different tools that rely not on their final flashes, but on the gravitational wake they leave as they drift through the cosmos. To find those larger primordial black holes that are not evaporating, we need to use gravity itself. The method is gravitational microlensing. Einstein showed that gravity bends light. When a massive object passes between us and a distant star, its gravity acts like a lens, focusing the star's light. The star appears to brighten and then fade over days or weeks. The duration of the brightening reveals the mass of the lens. A Jupiter-mass black hole produces a lensing event lasting days, while an asteroid mass one lasts only hours. The brightening is small, a few percent, but measurable. If primordial black holes make up dark matter, they drift through the galaxy in enormous numbers, occasionally passing in front of stars and creating temporary brightenings. Astronomers have been watching for such events. Surveys like ULGO, the Optical Gravitational Lensing Experiment, have monitored hundreds of millions of stars in the galactic bulge and Magellanic Clouds for over 2 decades. They have found thousands of microlensing events, but almost all are caused by ordinary stars, not dark objects. If a full dark matter halo of black holes existed, the expected event rate would be much higher. The data from OGLE and other surveys rule out primordial black holes in a mass range from about 10 to the -7 solar masses, roughly the mass of a large asteroid, up to about 10 solar masses. If black holes in that range made up all dark matter, we would have seen far more microlensing events. But a few intriguing events do not fit the standard picture. In 2020, a team using the Subaru telescope's Hypersuprime cam reported a possible microlensing event toward the Andromeda galaxy that lasted only a few hours, too short for a normal star. They suggested it could have been caused by a primordial black hole with a mass around that of a small asteroid, about 10 to the 20th grams in the mass range unconstrained by gamma-ray searches. The event was seen in only one filter, making it hard to confirm. Further analysis has been inconclusive. It remains a maybe, but it shows the search is not over. So microlensing tells us that if primordial black holes are the dark matter, they must be either much lighter than an asteroid or much heavier than a typical star. The lightest end is already constrained by Fermi. The asteroid mass range is partly ruled out, but a small possibility remains. That leaves the heavy end wide open, objects with the mass of stars or greater. And for those, we have a completely different instrument already pointed at the sky, listening for the one thing a black hole is famous for doing: merging. Merging black holes produce a distinctive chirp, a rising frequency as two massive objects spiral inward and collide in a burst of gravitational waves. Since 2015, LIGO and Virgo have detected dozens of these chirps, each announcing a merger in the distant universe. Many of these black holes had masses stellar evolution cannot easily explain. The standard picture is straightforward. A massive star ends its life in a supernova, and the leftover core collapses into a black hole. For stars born with the chemical makeup typical of our galaxy, that process produces black holes up to about 20 or 25 times the mass of the Sun. Yet LIGO kept seeing black holes in the range of 30 to 50 solar masses, sometimes higher. One event, GW1 1905-21, involved a black hole of 85 solar masses merging with one of 66, producing a final black hole of over 140 solar masses. A star that massive would have blown itself apart in a pair-instability supernova, leaving no black hole behind. These black holes exist, so either we are missing something about stellar physics or they formed another way entirely. That other way is the primordial channel. If a black hole forms from direct collapse in the first second after the Big Bang, there is no limit from stellar evolution. It could be any mass that fits within the horizon at that moment, including tens of solar masses. When LIGO sees a black hole in the mass gap, one natural explanation is that it formed before any stars existed. There is a second clue: spin. Spin is encoded in the gravitational wave signal itself. The waveform's shape and amplitude depend on how fast each black hole rotates. Astrophysical black holes from collapsing stars are expected to spin rapidly because the star was rotating and the collapse concentrates angular momentum. Primordial black holes, by contrast, form from density fluctuations in a nearly uniform expanding universe and inherit almost no spin. When astronomers measure the spins of LIGO's merging black holes, many are consistent with 0, the lowest measurable values. The median inferred spin for several events is below 0.1, a value difficult to achieve from stellar collapse even with low metallicity stars. Some events show spins so low they are hard to produce in any stellar formation scenario. The consistency across multiple events strengthens the case. Spin provides an independent constraint from mass, and both point toward a primordial origin. None of this is proof. There are alternative explanations. First-generation stars in the early universe had very low metal content, and their collapses might produce heavier black holes with lower spins. The sample is still small, and selection effects could bias the data. But the fact that a primordial explanation fits so well has forced the astrophysics community to take it seriously. Papers exploring the possibility appear regularly in major journals. Some researchers argue that a fraction of LIGO's black holes, perhaps a substantial one, could be primordial. What makes this compelling is that LIGO has given us the first direct evidence of black holes whose masses and spins align with the primordial hypothesis. Those chirps might be the first concrete signature of a primordial black hole. Future gravitational wave observatories like LISA in the 2030s may see even more, particularly in a mass range that stellar collapse cannot reach, which could settle the question. But if primordial black holes are real, a much closer and more personal question arises. What happens if one gets too close to Earth? If primordial black holes are real, they are out there, right now, drifting through the galaxy. Most of them are far from us, but every now and then, one might pass through the inner solar system, and occasionally, one might hit Earth. Think about what that would mean. The smallest plausible PBHs, with masses around that of a large asteroid, are only about 1/100th of a millimeter across. That is smaller than a grain of sand. If one of those struck Earth, it would not create a crater or a fireball. It would simply punch straight through the planet, tunneled by its immense density. It would leave behind a thin, glowing tube of plasma, briefly energized by the passage. The hole would seal itself almost instantly. The effect on the surface? Negligible. You would not notice anything. But if the PBH is bigger, say the mass of a small moon, things get interesting. That object, still microscopic in size, would release the energy equivalent of a large earthquake as it ripped through the mantle. The seismic waves would travel around the planet. Our global network of seismometers, built to detect earthquakes, might register an anomalous event. No known natural phenomenon produces a perfectly straight, high-speed seismic track moving through the entire Earth. It would be unmistakable. So far, we have not seen any such signal. That is not surprising. The number density of PBHs needed to account for dark matter is tiny. Even if they were abundant in the early universe, By now, the odds of one intersecting Earth are vanishingly small over human timescales, but the absence of a detection does provide a useful constraint. It tells us that PBHs larger than about 10 to the 21st grams cannot be too common. Otherwise, we would have noticed their passage. The point is not that we are in danger. The point is that different masses produce different, testable consequences. And the fact that we have not observed any of those consequences is itself data. It narrows the window. It tells us that if PBHs make up dark matter, they must be either very small, below the threshold where their effects become dramatic, or very rare. That is why the hunt continues. It is not that the hypothesis has been ruled out. It is that we have systematically eliminated the most obvious signatures. And in doing so, we have learned something about the possible mass range. The scenario also highlights why PBHs are so hard to find. They are incredibly compact. Their gravitational influence is only noticeable when they are close to something or moving through dense matter, and they do not emit light. So we have to rely on indirect effects. Gravitational lensing, gravitational waves, and yes, the occasional impact. None of these have delivered a clear yes yet, but they have delivered a series of no's that are gradually painting a picture of what a real PBH would look like. So PBHs are hard to catch in the act, but perhaps the most profound role they could play is not as a menace, but as a messenger from the dawn of time. If PBHs exist, they are the oldest surviving structures in the universe, formed before any star or galaxy. They have drifted unchanged ever since, making them a direct record of conditions at the moment of creation. A dinosaur fossil reveals an animal's size, diet, and environment. PBHs do the same, but for the universe when it was less than 1 second old. Their mass is set by the size of the collapsing region that gave birth to them. In the early universe, tiny density fluctuations could collapse directly into black holes, with mass proportional to their horizon mass at that moment. A PBH of 10 to the 20th grams tells us about fluctuations 10 to the minus 23rd seconds after the Big Bang. A solar mass PBH tells us about fluctuations a few thousandths of a second later. Each mass range is a different page in the early universe's diary. This is why PBHs contest cosmic inflation. Inflation predicts a nearly uniform distribution of matter with tiny quantum seeds. The precise shape of those seeds determines how lumpy the universe was. If the seeds were just right, they produce a specific number of PBHs at each mass. If the seeds were smoother, fewer PBHs formed. If more irregular, PBHs could have formed in abundance. By measuring the mass spectrum of any existing PBH population, we can directly compare it to inflation model predictions. No other observation can do that. The cosmic microwave background gives a snapshot of the universe at 380,000 years. PBHs give a snapshot at less than 1 second. There is another layer. PBH formation involves gravitational collapse in a quantum regime, so PBHs could reveal effects from quantum gravity. Some theories, like string theory, predict that the early universe could have produced exotic objects that later decayed into PBHs. If we see a mass distribution that cannot be explained by standard density fluctuations, it could be a signature of new physics. The energy scales involved are far beyond what the Large Hadron Collider can reach. PBHs are the only natural laboratory we have for those conditions. Even if PBHs contribute only a tiny fraction of dark matter, every detection or upper limit is data. Each null result tells us that the early universe could not have been too lumpy at that scale. Each possible candidate event gives a clue about the power spectrum. The stakes have changed. This is no longer just about explaining why galaxies spin too fast. It is about reading the fossil record of the cosmos. The search for PBHs is worthwhile regardless of the outcome. We are not simply hunting for dark matter. We are piecing together the universe's earliest history, one mass interval at a time. But if primordial black holes are real, we haven't seen the last of them. The null results from Fermi and the limited microlensing surveys only close specific windows. They don't shut down the entire hypothesis because the mass range where PBHs could still be all of dark matter remains largely unexplored. Roughly the mass of a small asteroid, around 10 to the 17 grams, up to 10 to the 22 grams. And over the next decade, several new experiments will begin probing that very gap. The most anticipated is LISA, the Laser Interferometer Space Antenna. Unlike LIGO, which detects gravitational waves from black holes tens of times the sun's mass merging in the local universe, LISA will operate at much lower frequencies. That lets it see much heavier black holes merging, but also lighter ones merging earlier in cosmic history. If primordial black holes exist in the asteroid mass range, binary systems of two such PBHs would have formed in the early universe. Those binaries would still be orbiting each other today, emitting a continuous gravitational wave hum that LISA could pick up. Some simulations suggest that if PBHs make up even a fraction of dark matter, LISA should see dozens of those signals. If it sees none, that mass range becomes strongly constrained. Meanwhile, the Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will perform the most ambitious microlensing survey ever attempted. Its wide field of view and months-long observing campaigns toward the galactic bulge will monitor hundreds of millions of stars. That gives it the sensitivity to catch the brief brightening from an object as small as an asteroid passing in front of a distant star. The Subaru HSC survey already found a handful of candidates, but Roman will cover an area 100 times larger and detect events that last only a few hours. If PBHs exist in the asteroid mass window, Roman should see a clear excess of such events. If it sees nothing, that window closes. On the gamma-ray front, new instruments could complement Fermi's silence. The proposed LIGO mission, or All-Sky Medium Energy Gamma Ray Observatory, would be far more sensitive to the diffuse gamma-ray background from a population of evaporating PBHs. Even if no individual PBH is caught in the act of final explosion, the cumulative glow from billions of tiny black holes might be visible. A detection of that background at the right energy and spatial distribution would be a powerful signal. And if a nearby PBH does explode, LIGO would see it as a bright flash, giving us a direct distance and mass measurement. Even pulsar timing arrays, networks of precisely monitored millisecond pulsars, could play a role. As PBHs form in the early universe, the rapid collapse of density fluctuations might produce a background of gravitational waves at nanohertz frequencies. Pulsar timing arrays, like nanograph, have already reported a possible gravitational wave background. Most explanations point to supermassive black hole binaries, but PBH formation could also contribute. The exact spectrum would be different, and as data improves, this becomes another cross-check. So the next decade will be decisive. Roman will test the asteroid mass window. LISA will probe the existence of primordial binaries, and advanced gamma-ray telescopes will look for either individual explosions or a collective glow. Each of these experiments is independent. They do not rely on the same assumptions. If any one of them finds a positive signal, it will transform cosmology. And if all return null, the viable mass range for PBH dark matter shrinks to near nothing. So the hunt is far from over. But what about the idea that PBHs might be hiding in plain sight, masquerading as something else in our data? For 40 years, the most popular dark matter candidate was a hypothetical particle called a WIMP. The logic was elegant. WIMPs would have been produced in abundance in the hot early universe, interacting only through gravity and the weak nuclear force. They could be found directly in underground experiments, indirectly through annihilation products in space, or even created at particle colliders. the search became massive. Underground detectors like Xenon, Lux, and Panda X waited for the faint recoil of a WIMP colliding with a nucleus. The Fermi Gamma-ray Space Telescope scanned the galactic center for the glow of annihilating WIMPs. The Large Hadron Collider smashed protons at unprecedented energies looking for new particles. After 2 decades of exhaustive searching, no unambiguous WIMP signal has ever been confirmed. The classic WIMP parameter space has been squeezed to near nothing. That silence opened the door for alternatives once considered fringe, including primordial black holes. Switching from a particle to a black hole as dark matter is not just a change of suspects, it is a shift in paradigm. WIMPs behave like a fluid. Primordial black holes are compact objects, each a point mass. This difference has profound implications. In a universe full of PBHs, dark matter would be clumpy on small scales, affecting the formation of the first galaxies, the orbits of stars, and gravitational lensing. In a universe full of WIMPs, dark matter would be smoothly distributed at small scales, only clustering on galactic scales. That is where observational constraints become crucial and where PBHs face their toughest tests. Taking the full suite of searches from microlensing to gamma rays to gravitational waves, only one narrow island of viability remains. Microlensing surveys found too few events for PBHs in the asteroid mass range. Gamma-ray observations ruled out evaporating PBHs below 10 to the 15th grams. Gravitational wave results suggest some black holes might have primordial origins, but cannot yet prove it. Between roughly 10 to the 17th and 10 to the 22nd grams, PBHs remain a possible candidate for all of dark matter. That window is small, about the mass of a small asteroid and largely unexplored. A 2021 paper argued that if certain assumptions about formation and clustering hold, even stellar mass PBHs could constitute all dark matter, though that claim remains controversial. So the comparison is not settled. On one side, the particle paradigm has decades of theoretical development and experimental infrastructure, but has yet to deliver a single confirmed detection. On the other side, the PBH paradigm is simpler in some ways. It does not require new physics beyond general relativity and quantum mechanics. But it must explain why we have not seen more direct evidence, and it struggles to account for the smoothness of dark matter on large scales as seen in the cosmic microwave background. Some researchers now propose a hybrid scenario. Perhaps most of dark matter is a new particle, but a fraction, say 5 or 10%, is primordial black holes. That small fraction might escape current constraints and could explain intriguing signals like the unexpected masses seen by LIGO or the gravitational wave background reported by pulsar timing arrays. In that case, PBHs would not solve the dark matter problem entirely, but they would still be real cosmic fossils, remnants of the Big Bang. The question facing cosmologists today is not which idea is right, but which can survive the next wave of data. But there is a twist. Even if PBHs are not the dark matter, they could still explain something else puzzling: the origin of supermassive black holes. Primordial black holes might also solve a puzzle that has been bothering astronomers. The supermassive black holes at the centers of galaxies, objects with masses of millions or billions of suns. The question is, how did they get so big so fast? We had detected quasars powered by black holes that already weighed nearly 1 billion solar masses when the universe was just 700 million years old, less than 5% of its current age. Standard theory says black holes form when massive stars collapse. Those stellar remnants start at a few tens of solar masses. To grow to 1 billion suns in such a short time, they would have to swallow gas at an extreme rate continuously, far exceeding what is known as the Eddington limit. That limit is the point where the outward pressure from inflowing radiation becomes strong enough to push gas away, shutting off further growth. Pushing beyond it is possible, but requires very specific conditions and is hard to sustain. This has become known as the too big, too fast problem. Primordial black holes offer a clean workaround. Imagine instead that a black hole with a mass of 10,000 or even 100,000 solar masses already existed from the very first second of the universe. That seed would not need to form from a star. It was there before any stars ignited. From that head start, it could begin accreting gas immediately. It could grow by merging with other smaller black holes. Even with moderate accretion, it could reach 1 billion solar masses within a few 100 million years, comfortably fitting the timeline. Consider the specific case of quasar J1342 plus 0928. Discovered in 2017, it hosts a supermassive black hole of about 800 million solar masses at a redshift of 7.54, when the cosmos was only 690 million years old. Under the stellar collapse scenario, the progenitor star would have collapsed into a black hole of maybe 50 or 100 solar masses. Then that black hole would need to grow by a factor of 10 million in less than 700 million years. That demands nearly continuous super-Eddington accretion. A primordial seed of, say, 100,000 solar masses would need to grow by a factor of only 8,000, which is much easier to achieve. The numbers start to fit. Of course, this is still a hypothesis. There are other ideas. Direct collapse of massive gas clouds could also produce heavy seeds. But primordial black holes add a unique twist. They tie the existence of supermassive black holes directly to the physics of the Big Bang. If true, then the monster at the center of our own Milky Way, Sagittarius, a star, might have started as one of these ancient objects. So the question becomes, how do we tell the difference between a primordial seed and a stellar remnant? The answer might lie in the distribution of black hole masses, their spins, or the way they affect their surroundings. If PBHs really did seed the first giant black holes, that would mean the very growth of galaxies was shaped by relics from the first second and could have left fingerprints on the large-scale structure of the universe itself. That fingerprint becomes even more intriguing when we tune in to the 21-centimeter line. This radio signal from neutral hydrogen maps the temperature and ionization of intergalactic gas billions of years ago. In 2018, the EGES experiment found that absorption signal nearly twice as strong as standard models predicted. The gas might have been much colder than expected, a result difficult to explain with ordinary dark matter. Primordial black holes offer a mechanism. Even a small fraction of dark matter in PBHs would accrete gas and release energy, heating the intergalactic medium in a way that deepens the absorption. Alternatively, concentrated PBHs could trigger early star formation, cooling the surrounding gas and increasing the absorption depth. The exact effect depends on PBH mass and abundance. Remarkably, the mass range that best fits the EGES anomaly coincides with the ultralight window around 10 to the 20th grams, which is otherwise extremely hard to test. That coincidence keeps the hypothesis alive, though the EDGE's result itself remains controversial and may have mundane explanations. Beyond the 21-centimeter line, PBHs leave other indirect fingerprints. Because they are discrete point masses rather than a smooth sea of particles, they create gravitational perturbations as they move. These perturbations can catalyze the assembly of early galaxies, making them form sooner than they would in pure particle dark matter. That ties directly to the supermassive black hole puzzle and the appearance of massive galaxies at surprisingly early times. But the same perturbations also leave imprints on the cosmic microwave background, which the Planck satellite measured with exquisite precision. Those measurements sharply constrain how much dark matter can be in PBHs across most mass ranges. For the ultralight window, Planck allows PBHs to be at most 10 to 20% of the total dark matter, but not all of it. The EG's hint combined with Planck suggests a scenario where PBHs are a minority component, perhaps 1% of the dark matter, coexisting with an unknown particle. These subtle influences are exciting. but they also mean that PBH models must pass many tests. So far, they have survived, but the window is narrowing. Neutron stars are city-sized balls of nuclear matter so dense that a teaspoon would weigh billions of tons. If a primordial black hole drifts too close, the neutron star's gravity can capture it. The PBH sinks into the core and begins accreting material, consuming the star from within. Over thousands to millions of years, the neutron star would be completely consumed, leaving a black hole of comparable mass. Alternatively, if its structure is disrupted, the event would produce a detectable burst of gamma rays or X-rays, possibly accompanied by a gravitational wave signal. Astronomers have searched for such events across the Milky Way and nearby galaxies. They have never seen one. This absence places an upper limit on how many primordial black holes exist in the asteroid mass range, roughly 10 to the 22nd grams and above. If PBHs that range were common, neutron stars should occasionally be destroyed. Their survival tells us that at most a tiny fraction of dark matter can be made of those particular PBHs. The limit is tight but not fatal to the PBH hypothesis. It mainly constrains a specific mass window. There are gaps where neutron star capture is less efficient. If a PBH is much lighter than about 10 to the 20th grams, its gravity is too weak to capture a neutron star effectively. If a PBH is extremely massive, many times the mass of the Sun, it would disrupt the neutron star's orbit before capture, and the event might appear different. So the neutron star method, like many others, rules out some possibilities, but leaves others open. Each detection method, gamma ray silence, microlensing outliers, LIGO's unexpected chirps, neutron star destruction slices away another piece of the allowed mass range. Yet a significant window remains roughly between 10 to the 17th and 10 to the 22nd grams. In that ultralight zone, PBHs could still make up a substantial fraction, perhaps all of the dark matter. They are small enough to evade Hawking radiation limits, dense enough to avoid microlensing detection, and light enough to slip through neutron star capture constraints. So far, every search has either found nothing or hints that remain controversial. This brings us to the key question. Could PBHs be hiding in the one mass range we haven't properly explored? After every constraint from gamma rays, microlensing surveys, LIGO, and neutron star captures, one mass window remains open. The ultralight gap from roughly 10 to the 17th to 10 to the 22nd grams. Hawking radiation eliminates any primordial black hole lighter than about 10 to the 15th grams. Those would have evaporated by now, and we would have detected their final flash. Microlensing surveys rule out black holes between 10 to the 22nd and 10 to the 30th grams as a major dark matter component. If enough existed, they would have distorted starlight in ways we can measure. Neutron star capture partially constrains the region near 10 to the 20th to 10 to the 22nd grams, but not completely. The gap between 10 to the 17th and 10 to the 22nd grams remains unclosed. A black hole in this range has a mass comparable to a small asteroid or a mountain, yet its event horizon is smaller than a proton. It is too massive to have evaporated, too small to produce a detectable microlensing event, and too light to be captured efficiently by a neutron star. It would be nearly invisible to every method deployed so far. Why is this gap so hard to probe? The signatures become extremely subtle at these masses. Hawking radiation is negligible. Microlensing requires a larger mass to measurably bend background starlight. Neutron star capture is inefficient because the black hole's gravitational cross-section is tiny. To find them, new approaches are needed. Femtolensing looks for interference patterns in the light curves of distant gamma-ray bursts when an ultralight black hole passes in front. That search has not yet been done systematically. Another method tracks white dwarf cooling. A passing black hole would heat the star from within, and anomalous cooling rates could set limits. And future gravitational wave detectors like LISA or Decisive might catch the rare merger of two ultralight black holes. This mass window is the last refuge for primordial black holes as a complete dark matter solution. Everything else has been ruled out or strongly constrained. If PBHs exist, they are most likely hiding here in a range we have barely begun to test. Could the most elusive objects in the universe be sitting exactly where we haven't looked effectively? And if they are, what would it take to finally see them? But there is another way to search for primordial black holes. One that does not look for individual objects, but for their collective gravitational effect on entire galaxies. If PBH make up a significant fraction of dark matter, they are not a smooth, diffuse fluid. They are point masses, compact bullets scattered through the halo. And those bullets would leave a mark on the delicate structures that trace the galaxy's gravitational field. Consider tidal streams. When a globular cluster or dwarf galaxy gets torn apart by the Milky Way's gravity, its stars stretch into a long, thin ribbon, a stellar stream. The most famous example is GD1, a stream that wraps around our galaxy in an almost perfect arc. Its width is only a few hundred light-years across, and it has been undisturbed for billions of years. That narrowness is a gift to astronomers. If a massive compact object, like a 10,000 solar mass black hole, passed close to the stream, its gravity would kick some of those stars out of alignment, creating gaps or thickening the stream. Teams have looked for exactly that signature. Using data from the Gaia satellite, they have searched for gaps and wiggles that would betray a passing PBH. So far, they have found none of the expected disturbances. This places a strong constraint. PBHs heavier than about 10 to the 5th solar masses cannot make up more than a small fraction of dark matter. If they were abundant, we would see the damage. The same logic applies to globular clusters. These dense balls of stars are also sensitive to gravitational heating by passing black holes. If too many PBHs drifted through, they would gradually puff up the clusters, making them larger and more diffuse than we observe. The observed sizes of globular clusters therefore set an upper limit on the density of compact dark matter objects in the halo. Again, the limit is strongest for the largest masses. But here is the critical point. All of these constraints weaken dramatically as the PBH mass decreases. A black hole, the mass of an asteroid, the kind hiding in the ultralight gap, has an event horizon the size of a proton. Its gravitational influence on a star is negligible unless it passes within a few thousand kilometers. The chance of such a close encounter with any star in the Milky Way over billions of years is vanishingly small. So while these galactic dynamics tests have closed the door on PBHs heavier than about 10 to the 5th solar masses, they say almost nothing about the mass range where PBHs could still be the dark matter. The galaxy's most delicate structures are simply not sensitive enough. This means that even after a decade of meticulous surveys, the ultralight window remains wide open. We have ruled out many possible hiding places, but not all. The search continues, but we have to look in a completely different way. The integral satellite has detected a faint glow at exactly 511 kilo-electron-volts from the galactic center, the unmistakable signature of electron-positron annihilation. The source of all those positrons remains unknown. Supernovae produce them, but not enough. Millisecond pulsars could be responsible, but the signal distribution does not align perfectly. Annihilating WIMP dark matter is another candidate, yet after decades of searching, none of these explanations has been confirmed. Primordial black holes offer a more exotic possibility. If PBHs with masses around 10 to the 16th to 10 to the 17th grams exist, they would be finishing their evaporation right now via Hawking radiation, producing all sorts of particles and antiparticles, including positrons. A population of such PBHs near the galactic center could naturally produce the observed positron excess, and the predicted gamma-ray spectrum would match the 511 keV line almost perfectly. This hypothesis connects two separate mysteries: the origin of the positrons and the existence of PBHs in a mass range that is otherwise hard to test. But the same PBHs that produce positrons also generate gamma rays at other energies. Observations from Fermi and other telescopes have placed strict limits on the number of such low-mass PBHs across the galaxy. To explain the 511 keV signal without violating those constraints, the PBHs would need to be strongly clustered in the galactic center and their overall abundance finely tuned. Compared to conventional sources like supernovae and pulsars, the PBH explanation is far more speculative and requires special conditions. Most researchers consider it a long shot, yet the possibility will not disappear entirely. It forces us to consider that unexpected connections between cosmic puzzles are always possible, even if improbable. The careful balancing act between all these constraints continues. That balancing act, however, applies only to the PBHs we can test with telescopes. But there is another level to this story, one that reaches beyond astrophysics into the deepest foundations of physics itself. If primordial black holes exist, especially the smallest ones, they are the only objects in the universe where quantum gravity effects become directly observable. Why? Because they are small enough that their behavior is governed by both general relativity and quantum mechanics simultaneously. For a star-sized black hole, quantum effects are negligible. But for a PBH weighing only a few billion tons, the event horizon is smaller than an atomic nucleus. At that scale, the curvature of space-time is extreme, and the rules of quantum field theory start to break down. This is where Hawking radiation becomes more than a clever prediction. It is a real quantum process, a direct signal from the interplay between gravity and the quantum world. If we could detect a PBH evaporating today, we would be watching a process that inherently requires a theory of quantum gravity to fully describe. No particle accelerator on Earth can reach the energies where quantum gravity becomes important. A PBH would be nature's own laboratory. Now, string theory, the leading candidate for a quantum theory of gravity, predicts something even more intriguing. Many string theory models require extra dimensions of space, curled up in shapes so small we cannot see them directly. In the first moments after the Big Bang, those extra dimensions could have influenced how density fluctuations grew. Some models suggest that the collapse of certain heavy particles called moduli, predicted by string theory, could produce a population of PBHs with a very specific mass range. Others propose that PBHs could have formed directly from the energy released when extra dimensions stabilized. This is extremely speculative. No experiment has confirmed string theory or extra dimensions, but the connection is tantalizing. If we ever detect a PBH, its mass, spin, and abundance could provide the first empirical hints about the geometry of extra dimensions, something particle colliders may never achieve. It would be a convergence of two of the most profound mysteries in physics: the nature of dark matter and the quantum structure of space-time. Could the shadows of primordial black holes hold the key to the quantum nature of space and time? It is a possibility that pushes the search far beyond dark matter into the very fabric of reality, and it remains an open question. That open question, however, needs evidence. And in 2020, a team using the Subaru telescope in Hawaii thought they might have found a piece of it. They were conducting a microlensing survey of the Andromeda galaxy, looking for the brief brightenings caused by a compact object passing in front of a distant star. And they found exactly one event that fit the profile of a primordial black hole in the ultralight window. Its duration was roughly 0.3 seconds, which corresponds to a PBH mass of about 10 to the 21st grams. That is squarely in the mass range where primordial black holes could still be all of dark matter. The result was electrifying. For the first time, it looked like we might have caught a direct glimpse of one of these ancient fossils. The team published their analysis, careful to note the statistical limitations. A single event, after all, is not a discovery. The probability that it was a fluke caused by background noise was not negligible, and other explanations were possible. A rogue planet, not bound to any star, could have produced a similar microlensing flash. So could a binary star system that happened to align just right. Still, the event was consistent with a primordial black hole, and it was in exactly the mass range that other searches had not yet ruled out. The astrophysics community responded with both excitement and heavy skepticism. Many pointed out that if PBHs made up all dark matter, the expected rate of such microlensing events in Andromeda should have been higher. One event, on its own, was tantalizing but not enough to overturn decades of null results. A follow-up survey with more observing time failed to find another such event. That did not disprove the existence of PBHs, but it shifted the odds back toward the null hypothesis. The original event remains on the books as an unexplained anomaly. It could be a genuine hint, or it could be the statistical fluke that any search will eventually produce. That is where the controversy sits today. A single, fleeting flash that might have been the first direct detection of a primordial black hole, but which could just as easily be nothing more than cosmic noise. It is a perfect illustration of the scientific process at work. A tentative claim subjected to scrutiny, requiring more data. The search continues. And that unresolved flash is exactly the kind of signal that the next generation of telescopes, like the Roman Space Telescope, will be designed to confirm or rule out. For now, the question remains open. Was that faint flicker in Andromeda a glimpse of the universe's oldest inhabitants, or just another ghost in the data? A clear, repeatable microlensing signal from a compact object, too massive for a planet or star, would confirm primordial black holes. The immediate implication: dark matter would be accounted for by these ancient black holes. But the deeper prize is a direct window into the first second of the universe. Every primordial black hole's mass is set by the scale of the density fluctuation that collapsed. Finding them in a specific mass range would test inflation models directly, probing energies no particle accelerator can reach. It would also verify Hawking radiation if we catch tiny ones near the end of their evaporation, watching them explode in real time and observing quantum effects at the edge of a black hole for the first time. That would be the first experimental test of black hole thermodynamics, a purely theoretical field until now. As for practical risk, Earth would be hit by a primordial black hole about once every few million years. The smallest would punch straight through, leaving a trail of energized particles but no lasting damage. Larger ones could trigger seismic waves but are exceedingly rare. The hazard is negligible compared to asteroid impacts. If the next detection is real, it would be a turning point for our understanding of the early universe, quantum gravity, and observation itself. It would rank with the first detection of gravitational waves or the Higgs boson. But let us be honest, we have not found one yet. So where does that leave us? After decades of searching through gamma-ray data, stellar microlensing, gravitational wave signals, and galaxy dynamics, the evidence tells us that primordial black holes cannot account for all of dark matter in most mass ranges. Fermi has not seen a single Hawking explosion, ruling out any significant population of black holes smaller than about 10 to the 15th grams. Microlensing surveys like Ultralight and Subaru Hypersuprime Cam have tightly constrained PBHs in the asteroid mass range up to around 10 to the 22nd grams, finding far too few events to explain the missing mass. LIGO shows that black holes between a few and 100 solar masses exist, but their merger rates and spins do not clearly point to a primordial origin, and they cannot be abundant enough to account for all dark matter. Neutron star captures and galactic dynamics add further exclusion zones. The allowed parameter space has been squeezed from almost every angle, but it has not been squeezed to zero. One narrow gap remains stubbornly open. Between roughly 10 to the 17th and 10 to the 22nd grams, no current experiment can rule out primordial black holes as the dominant form of dark matter. This mass range spans from a small asteroid to a small moon. That window is tiny in absolute mass, but enormous in implication. If PBHs exist there, they would be invisible to every detection method deployed so far. They would be too small to lens starlight effectively, too large to evaporate, and too sparse to affect neutron stars. They would be the perfect dark matter particles, except they would not be particles at all. They would be black holes, and they would be everywhere. The scientific community is divided on whether this remaining window is promising or wishful. Some theorists point out that it requires very fine-tuned conditions in the early universe to produce PBHs in just that mass range. Others argue that the same fine-tuning applies to particle dark matter models and that PBHs have the advantage of being a purely gravitational candidate requiring no new particles or forces. The debate is healthy and active. What matters is that the question is now testable. The Nancy Grace Roman Space Telescope, set to launch in the late 2020s, will perform a wide-field microlensing survey that can probe the ultralight window directly with orders of magnitude better sensitivity than current surveys. LISA, due in the early 2030s, could reveal a population of binary PBH mergers with a distinct pattern from stellar origin: black holes. New gamma-ray telescopes like AMI-GAO could detect the diffuse glow from a background of slowly evaporating PBHs near the lower end of the window. The hypothesis has not been confirmed, but it has not been ruled out either. The coming decade will likely decide. The answer, yes or no, will reshape cosmology. Primordial black holes are not merely a candidate for dark matter. They are the ultimate cosmic fossils, carrying a direct signal from the first second of existence. Every other object we study formed millions or billions of years after the Big Bang. A primordial black hole, if it exists, was born within that first second. It holds an imprint of the density fluctuations, the energy scales, and the physics that governed the universe when it was smaller than an atom. No particle accelerator can probe those energies. No telescope can look back that far directly. But a primordial black hole is a messenger that has survived for nearly 14 billion years, waiting to be found. Searching for them is an act of cosmic archaeology. We dig through the noise of gamma rays, the flickering of distant stars, the echoes of gravitational waves, hoping to find a signal from the beginning. Even if we never find one, the search refines our understanding of the early universe, quantum gravity, and the limits of observation. Every null result tightens the constraints. Every unexplained event sharpens the question. The hypothesis is being tested on multiple fronts simultaneously. Within a decade, perhaps sooner, we will have our answer. That answer will be profound. If primordial black holes are real and make up the dark matter, the universe is filled with invisible relics of its own birth. Dark matter becomes gravity concentrated into points that have been drifting since before the first star ignited. If they are not real, we learn that the early universe was smoother than we thought. That black hole formation from density fluctuations is rarer than we guessed, and that dark matter must come from something else, perhaps an undiscovered particle, or a property of space we have not yet understood. Either outcome teaches us something essential. The possibility that we are surrounded by the oldest objects in existence, older than any star, older than any galaxy, older than the atoms in our own bodies, is humbling. It reminds us that the universe still holds secrets from its first moments. We are still learning to read them. This is the quiet before a potential breakthrough. Subscribe to follow the real-time hunt for these cosmic fossils and explore the deepest mysteries of space and physics. Before you go, I have a question. If you could choose between primordial black holes or a new particle as the explanation for dark matter, which would you bet on and why? Let me know in the comments.